Is it filming?
Yep.
All right, well, welcome back, Chem 125. So this is the second of 3 videos for oxidation reduction, also known as redox chemistry. So in the first video, we just went through the basic definitions. Oxidation is loss of electrons, put them on the right side. Reduction is gain, put them on the left side. You add them together, the electrons gained must equal the electrons lost. And then if you have an acid, you have as much H plus and as much H2O as you wish to use. You use them as you see fit. I want to start to get a little more realistic now. Something that's a little bit more complex. This is a redox problem that appears in every general chemistry textbook ever. So what I want to do is make it a bit more realistic from the way it's usually presented in a textbook, and it's the way we present redox in lab. So what I want to do is, if you notice here, these are all written as ions, and you know enough about ionic compounds that you just don't have a jar of Fe2+. You have to have a counter anion. Similarly, you need a counter cation here, counter anions here and here. So just for the sake of argument, I'm just going to make a couple of assumptions. So assume that chloride and sodium cations are your spectators. Okay, you know all about spectators in the metathesis lab that you already did, so I'm not going to bother going through that. Also, we just kind of always throw out there, assume it's in acid. Well, what acid? Is it hydrochloric acid? Is it acetic acid? Is it sulfuric? And what acid are we talking about? So let's actually use a specific acid. Let's keep it simple here. Assume hydrochloric acid is the in acid. Whenever you read that, let's actually use a specific acid rather than just arbitrarily tossing in H+. So I'm going to make this problem slightly more complicated, but you can go through this. So if we wanted to write this in a more realistic fashion, this would be iron 2 chloride in aqueous solution reacting with sodium dichromate in aqueous solution to produce iron 3 chloride in aqueous solution plus chromium 3 chloride in aqueous solution. Okay, now I'm not going to go through all this, but if you're presented a problem where you see the spectator ions, the first step you want to do is to eliminate the spectator ions and go right to the bare equation that shows you actually what's undergoing oxidation or reduction. Spectators, by definition, are not undergoing any chemical changes. So this shows you the basic chemistry. This is more realistic because it's actually what you would use in lab. So for now, I'm going to skip this part. Just be able to go from here to here by eliminating your spectator ions. And you'll notice there's no sodium on the other side. Where are we going to get that? Well, we're going to get that by combining sodium and chloride at the end. So we'll get there. So let's go right to what you already know how to do. I'm going to do this very quickly. So you've got iron becoming iron plus 3. Well, that's pretty straightforward. That's one of your half reactions. So iron plus 2 going to iron plus 3. It doesn't get much easier than that. What do we do? We're going up in charge, which means we're losing an electron. So I guess that means we have to put an electron on that side. And this is our oxidation half reaction. I like to emphasize that it's a half reaction. So it's not just an oxidation reaction, it's an oxidation half reaction, because you have to have, by definition, then a reduction half reaction. So the other one, the dichromate into chromium plus 3, must be your reduction. It has to be. All right, well, let's do that one. You'll see this particular reduction half reaction 5 or 6 times in this class. So hopefully you see this and you can just do it automatically. Cr2O7, 2 minus, leave a little space, chromium plus 3. Students often overlook the first step is to make sure that your non-hydrogen oxygen atoms bounce. You get 2 chromium, so we have to put 2 here. Okay, that's fine. 7 oxygens. Remember, you have as much water as you like. So we put 7 waters over here. And then we just added 14 hydrogen atoms to the right side, so the way we balance that is using protons, the from acid or in acid. Okay, so I think that's right. Now we have to balance the charge. Okay, up here the charge is +2 on each side, and that works. Here, the total charge on this side is +12, I think. How did I get that? 2 negatives and 14 positives is 12 positives. And over here it's, that's 0, +6. And I have electrons, so I've got to basically take this down by 6 to make each side +6. And the way we do that is by putting 6 electrons right there. Great. Okay, I'm going to need some more space. I'm going to erase this. Remember, electrons lost have to be equal to electrons gained, and that's not the case. But you have every right, and it's not violating any principles of thermodynamics. In fact, it's reinforcing them, to simply boost the coefficients of either half reaction by whatever you need to. So in this case, we're going to boost it up by a factor of 6, so that we have 6 electrons lost equals 6 electrons gained. In fact, they're the same electrons. That's important to remember. And I'm going to go right to the final answer. I'm going to put the spectator ions back in. And I like to do these where I rewrite things in the order that they're written and then add everything else after that. So we've got, let's see, let's go through. So iron, we'll have 6 iron +2, so that's going to be 6 FeCl2 aqueous. That's right. Okay. And then the dichromate, we'll only have one of them. Let's put the sodiums back in. Plus Na2Cr2O7 aqueous. Okay. Plus, let's see, what else am I'm doing everything on the left side of the arrow, so what else do I need? I need the hydrogen ions, or the protons. But remember, it's HCl, so we're going to make that 14 HCl. All right. Go to the other side. I think we're done there. So we're going to have 6. All right, that looks good. And then chromate, so +2 CrCl3 aqueous plus 7 waters. Now, again, there's just one problem here. Let's check this out for a second. Well, obviously, we need sodium. So we need 2 sodium atoms on the other side. And we have sodium and chloride as much as we want. So what we're going to do to balance this out, we're going to just take +2 NaCl in aqueous solution. Now, if thermodynamics does work, everything should balance now. Everything should balance. So you have 6 irons, 6 irons. Chloride, there's a whole bunch of them. 12 plus 14 is 26. Okay, so it's 26 chloride, so we've got 18 there, plus 6 more is 24, well, plus 2 more that we had to add in, so I think that works. So it has to work. Sodium, there's 2 on each side. Chromium, there's 2 on each side. Oxygen, there's 7 on each side, yes. And then 14, yeah, so that works. Did you get all that? Mm-hmm. Okay, so that's a slightly more complicated example. The thing we want to is, I think you all can do these steps. Boom, 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 without the spectator ions, because that's typically the way it'll be shown in a book. But in lab, we have to account for the spectator ions, because we're dealing with real chemicals, not just the stripped down ions. So that's how we're going with this one. And I think that is it for Redox number 2. Redox number 3, we'll be using Redox to do actually an analysis, an iodometric analysis of sodium hypochlorite in bleach which gets pretty complicated, but instead of doing those reactions, I'm going to do something that's analogous to it. So you have to do those on your own, but I'll show you one that's analogous and to make you take responsibility for transferring that to the lab. So we'll see you on video 3.